And we're back. We're going to solve a rational inequality. I have two examples to do with us here. So a rational equality is the same as a polynomial inequality. It's just that when we deal with rational functions and expressions, the denominator is not allowed to equal 0 because that would, of course, give us an undefined value. So we have asymptotes and wholes that occur when the denominator is equal to 0, and we have to consider those values as well. So again, same steps. Disregard the inequality symbol. Treat it like an equal sign while we're solving. We want it one rational expression equal to 0, and we want that equal to 0 on the right. So the rational expression is on the left. And what's really important is in a lot of situations, we need to make sure that it is one rational expression. So we may have to add or subtract those together. So we'll still go about getting critical numbers the same way, but we do have to pay attention to the numerator being equal to 0, which gives us zeros, and the denominator equal to 0, which lets us know where we have undefined values, and specifically vertical asymptotes, because the graph often changes direction at those vertical asymptotes. So we'll again choose test values, and we'll check each test value in the original inequality to see if we get a true or a false statement. And we're going to write our answer in interval notation. If the values from the numerator, we can determine whether or not we're going to use a bracket or a parenthesis, because we'll look at the inequality symbol, because if it's from the numerator, it's a 0, and that means it can be touching. And so we have to think about what the problem is asking us, greater than or equal to versus just greater than. With the equal to would be touching, without the equal to would not be touching. But when the value comes from the denominator, that represents an undefined value, which is likely a vertical asymptote. And you can't touch a vertical asymptote. So you would have to use parentheses there, even if the inequality symbol in the function suggests that you could touch it. All right, so we've gone over our steps. Here we have an example that we're going to work on. So as I said up above, we're going to make sure that everything, all the numbers are on the left side of the equation. So this is x plus 1 over x minus 2 minus 3. And we want to know where this is greater than or equal to 0. So that greater than or equal to 0 just lets me know we can be above or touching the x-axis. So in order for me to solve and get my critical numbers, I need this to be one rational expression, which means I need to add those terms together. And in order for me to add those terms together, I have to get a common denominator. So here I have x plus 1, x minus 2. I'm going to take that 3 and multiply it by x minus 2, x minus 2. And now I can add the numerators together. I have x plus 1 minus 3x plus 6 over x minus 2 equals 0. And combining like terms, I now have negative 2x plus 7 over x minus 2 equals 0. All right, so we have one rational expression on the left equal to 0 on the right. So we find our critical numbers. My 0 will come from setting the numerator equal to 0. So one of my critical numbers is going to be x equals minus 7 divided by negative 2, positive 7 halves. And my undefined value comes from the denominator equal to 0. So we have x cannot be 2. So looking at this, we'll plot it on the number line. I have two critical numbers, and these two critical numbers are going to break my number line into 3 pieces. 2 is going to go on the left because 2 is less than 7/2 or 3.5. And so this has created some intervals for me. I have -infinity to 2. And I'm going to go ahead and, even though my problem says equal to in it, I can never touch negative or +2 because it's a vertical asymptote. It's undefined. My next interval would be 2 to 7/2. And then my last interval, 7/2 to infinity. And because this is a 0, we can touch. So we might use a bracket, a square bracket here when we start writing our solution set. Okay, so we pick a test value on each interval. I would choose x equals 0, x equals 3, and x equals 4. And I'm going to test these. We can come back up and test them in the original inequality. I can test them in the second inequality I found. Either one works. If I plug in 0 to the original one that's typed on this page, I got 0 plus 1 over 0 minus 2 greater than or equal to 3, which is -1/2 is greater than or equal to 3. And we all know that -1/2 is not greater than or equal to 3. So that region is not going to be included. So we'll do the same thing with 3. 3 plus 1 over 3 minus 2 greater than or equal to 3. So that gives me 4 over 1. Positive 4 is greater than or equal to 3. This is true. And then lastly, I would say 4 plus 1 over 4 minus 2 greater than or equal to 3, which gives us that we have 5/2 is greater than or equal to 3, which is false. So there's only one region we can include in our solution set, and that region is the area in the middle between 2 and 7/2. So now when I write this, I can't touch 2 because it's a vertical asymptote. So I'm going to say 2, but I can touch 7/2 because it's a 0. So I use a bracket because that was what was indicated by the original inequality. So x is some number in this set from 2 to 7/2, can't equal 2, could equal 7/2. So let's do one more rational inequality, and this one is already in relation to 0. So my critical numbers, I can just grab those from looking at it. And the reason it's already got 0 on the right, there's nothing I have to simplify. It's one expression. So here I might get x equals 0, and from the denominator, we know that x cannot equal -6. So we'll plot these on our number line. -6 needs to go on the left, and 0 goes on the right. So choosing a test value for each interval, I'm going to choose x equals -7, x equals -1, and x equals +1. -7 squared over -7 plus 6. That's a positive over a negative, which gives me a negative value, which is less than or equal to 0. So this region is a go. Negative 1 squared over negative 1 plus 6. Here we end up with positive over positive, and positive is not less than or equal to 0. That's a false statement. So we cannot include that region. And then we've got 1 squared over 1 plus 6. So we've got 1 over 7, positive over positive. This represents a positive value. And a positive value is never going to be less than or equal to 0. So we can't include that region either. So it appears that only to the left of negative 6, not including negative 6, would be part of our solution set. But there's a little bit more to think about here. So remember, x equals 0 on our graph right here. This represents a 0. And a 0 is somewhere where you are touching the x-axis. So let's think about what this graph maybe looks like. And if you were to graph x squared over x plus 6, if you went to your y1 and said x squared, that's not how you do a squared, x squared divided by x plus 6, the graph you would get would look roughly like this. It has a oblique asymptote, a vertical asymptote at x equals negative 6. So we get something that looks like this. Got our oblique asymptote there and our vertical asymptote. All right, and so this is saying, where is the graph less than or equal to 0? Well, clearly to the left of negative 6, everywhere over here, we are below the x-axis. But equal to 0, we are touching the x-axis right at that one value. So in this situation, when we write our solution set, we say that x is in the set from negative infinity to negative 6. We can't touch negative 6. Union, and this is a special way that we write this, but we're just going to say we're only touching at x equals 0. So there's my answer there, this piece in the box. And I hope that helps.